Thank you, Sean, and thank you everybody for coming today. I know that this is one of the later installments of the Super Logic group, and I wanted to take the opportunity to thank Sean, Shay, and everybody that has taken any sort of part in organizing this. It has been extremely nice for me. It has kept me company among the pandemic. So today we are going to be presenting this little talk, which is a very drafty version of some thoughts that we have collected into a paper somehow, the three of us, regarding a follow-up to a previous paper that we had published in the Australasian Journal of Philosophy some years ago. And in that paper, we dealt with the problem of establishing completeness via the standard direct argument by Kalmar, which is very useful because it allows you to prove things without appealing to any sort of reduction or anything. It's a very constructive sort of proof in a certain sense. So we prove the completeness of a certain logic, certain very similar logic to LP from the point of view of a non-classical meta theory, right? So we were using a non-classical method based on naive comprehension and all of this sort of stuff. And today we are going to try to go beyond the bounds of the propositional level, which was what we focused on before. So we are going to try to see if the problem makes sense, or if in some version the problem can be solved for the case of first order logic. And then Zach is going to begin, and then I'm going to take over the more technical part of the talk. Okay.
Okay. Thank you, Gia. So hello, everybody. Nice to see you all. Everybody hear me? Yes, good. Okay. So back in March, Gia came to visit here in New Zealand. It was like March 11th. And he said, oh, you know, I don't know if I should come. And I said, what are you talking about? It'd be fine. You know, just get on a plane. Like and it turned out it was pretty much the last possible time anybody will probably be visiting here for a while. So it was good. And this is what we talked about while he was here. And then we've been talking about it since. So let's just warm up and start with a question or bold claim. So formal logic, a formal logic, gives some theory of validity. There's this thing called validity, and we want to theorize it. And we give such a theory about what deductively follows from what. Those formal logics then have properties. And when we want to study those properties in a precise mathematical way, then we're doing what's called metatheory, or I think a more old-fashioned for this is metamathematics. I don't know if anybody uses that anymore, but it's around the time of Hilbert and things called metamathematics, where we study what properties a logic has. For example, whether the logic is reliable in some precise sense. And those are really good things to know about your logic. So the question is, those facts that you establish in a metatheory are themselves proven by valid arguments. You argue them as theorems, which means that they're supposed to be deductively certain. So they're valid according to what logic? So there are many logics these days, and it's reasonable to ask, when you prove that a logic has such and such a property, what logic are you using to prove those meta facts with? So we're interested in that. So let me set the target that Gia is then going to go into detail about dealing with. And we're going to talk about what I'm going to call the big three. So there are these big three theorems of classical metatheory. As far as I know, nobody else calls them the big three, so don't go away from this and think, oh, you know, when I go and want to talk to the cool kids about logic and I just refer to the big three, they'll know what I'm talking about. But we're going to call them the big three for the purposes of this paper. This is this little trio of theorems that were proven in the 1920s or around 1930 that are the big classical theorems of metatheory. So Gödel proved the completeness of first order classical logic in his PhD thesis when he was, I think, 24. Was he 24?
Yep.
So that's pretty good. So the completeness of first order logic, classical logic, is that if an argument is semantically valid, then it is proof theoretically valid. In 1930, it was proved the compactness theorem that if every finite subset of a set of sentences is satisfiable, then the whole set of sentences is satisfiable. And a little earlier, actually, the Löwenheim-Skolem theorem, so logics have the Löwenheim-Skolemness property. In 1922 or so, they proved that if a theory has a model with an uncountable domain, then it has a model with a countable domain. And those are well-known, famous theorems of classical metatheory that if you ever take, the second course in logic in a classical sort of strain, that's what you would learn. And those are neat theorems. So these together, in some sense, characterize classical first-order logic. Classical first-order logic is, in some sense, the strongest logic that has these properties. They also, to some extent, show some limitations of classical first-order logic. In particular, the Löwenheim-Skolem theorem. When Skolem saw this, he didn't call it a theorem, he called it a paradox. We've since learned better. But these are really important things to know about first-order logic. So where are we coming in? Notice all of these are, when we give them informally, when we state them in English or in mathematical natural language, they're stated as conditionals. So the completeness theorem, for example, says if an argument is semantically valid, then it is proof theoretically valid. So one of the things we want to think about today, if you like, is what does a completeness theorem actually say, or what are we actually proving when we prove a completeness theorem? Are we proving a statement like this, right? If every finite subset is satisfiable, then the whole set. If a theory has a model with an uncountable domain, then it has a model with a countable domain. These look, in a way, kind of arresting or shocking at first, especially the compactness theorem. I don't know, the first time I saw the compactness theorem, I couldn't believe it. That sounded wrong. But let's stop and ask what the if-then is in these statements and see whether they prove what it sounds like they prove, because that's one of the things we're going to be investigating. So once we look at the proofs, the actual arguments that establish the facts, it may turn out, depending on your view, that actually what was proved is something a little bit more mundane that then is expressed in a logically equivalent statement that sounds cooler or sounds more shocking. But the proof itself is more straightforward. So for example, the compactness theorem might say that if every finite subset of a set of sentences is satisfiable, then the whole set is. So that's written as a conditional. That's the material conditional. P implies Q. But the reason for that is because if the whole set of sentences is inconsistent, well, then it has to be inconsistent somewhere. So that's the contrapositive. And often what one finds in metamathematics, in mathematics aboard, is a lot of times what is proven, the proof is a contrapositive proof. It proves the contrapositive, and it's easier to prove the contrapositive, and then you get to state it in the positive direction, and it sounds kind of shocking. But actually, if this is a material conditional, then that contrapositive is really just because either, for any set of sentences, the whole set is either consistent or it has some part that's inconsistent. It's just a disjunction. So it sounds like a conditional, but when you look at it, it's a disjunction, and that's still interesting, but perhaps maybe not as shocking as it initially sounds. Anyway, that's what we want to think about today, is what do these proofs actually prove? All of these three statements are logically equivalent. So you might be saying, what is he making a distinction here about? These are three ways of saying the same thing. There are three ways of saying the same thing logically in classical logic, but when you move to a non-classical setting, things that were equivalent sometimes no longer are, and sometimes they are, so you have to check. So in particular, we want to focus on the material conditional, which is being used in these proofs. I don't need to tell this audience that, some people have been unhappy with the material conditional. The material conditional is defined as not P or Q. And really, since its inception, smart people have been raising some doubts and concerns about it. And it's fun to show these things to undergraduates, right? Just two of our favorite examples. It comes out as a valid argument that if it's false that if God exists, then the wicked will be rewarded. That's true, but it follows from that deductively in classical logic that God exists. And that's surprising. That would be a surprising proof. Or just pick any three random sentences off the internet, P, Q, and R, any ones you like. If it's not the case that P implies Q, then it follows deductively that Q implies R. And if you have even the faintest relevantest bone in your body, there's something kind of wrong with that. So these, what's the point here? These big three metatheorems that are stated as conditionals, they're actually stated as material conditionals. And if there's something wrong with the material conditional, then we should at least pause and think about whether it's right to phrase them as natural language conditionals. So let's focus in on our target a little bit more. At the end of a widely used textbook on non-classical logic, which I know a bunch of us use for teaching at various times, the author Graham Priest writes, so this is in the very end of the book, in the methodological coda. Priest says, so it may be fairly asked what logic I've been using to specify and reason about the various logics we've been dealing with. The procedures employed haven't been formal ones, of course. Like most mathematics, matters have been left at an informal or kind of quasi-formal level. Now, of course, they could be formalized in classical logic, but someone like an intuitionist or a committed paraconsistent logician who takes classical reasoning to not be correct, well, for them, at least in part, you can't just leave things like that. Eventually, the non-classical person must kick away the ladder, so to speak. So Priest is pointing out that, for example, his preferred logic, LP, right, whenever it's presented, it's provided a model theory, it's provided truth tables, it's provided sometimes something like a proof theory, it's provided, at least in Priest's book, it's provided tableau method, which he calls a proof theory. We can debate that if you like. But it's provided, a mathematical apparatus, and then it's proved that these two bits of formalism relate to each other in the right way. Priest proves the completeness of LP proof methods with respect to their semantics. And any logic, this is a sine qua non for any would-be logic. If you referee papers, they almost always involve a soundness and completeness result for the proposed logic. But the issue Priest raises is not like an idle curiosity. Priest is a committed paraconsistent logician. He, in some sense, thinks LP is the correct logic or something like that. And anybody who thinks a non-classical logic is the correct logic can't just accept, or I'm going to say, can't just accept the classical proof for soundness and completeness. Adherents of a logic would be well within their rights to expect a proof to hold up in their preferred logic. And let's focus on the paraconsistent case. If someone is committed to the paraconsistent logic LP as something like a basis for correct reasoning or something that governs the norms of good reasoning, well, then you can't use a whole bunch of standard inferences. Logion, disjunctive syllogism, or this is material detachment, or modus ponens for the material conditional. You can't use modus ponens for the material conditional if you think there could be some contradictions, or you can't really argue contrapositively in the sense that if Q validly follows from P, you can't flip that around and say that not P validly follows from not Q. The turnstile for LP doesn't contrapose. So the strategies one often finds in the classical proofs for, say, metamathematical theorems can't be employed. These don't figure into valid proofs. The standard proofs do use all these principles. So if you go and look at them using your favorite logic LP, you might stop and ask, well, wait a second, what really is the status of these famous meta-theorems, or what is the status of the completeness of my favorite logic? Just because there's a classical proof of it doesn't necessarily give me a good reason to believe that it's complete. So these days when you prove completeness, so Gödel proved the completeness of first order logic in 1929 in his PhD thesis. It looks like historically, at the time, most people didn't understand his proof, or it wasn't widely taken up. And that's largely because it's a really, I'm going to say tedious, or it's a very syntactically heavy proof. And it doesn't necessarily show, it's not elucidating in the sense of showing you the reason necessarily that the result holds, unless you can really follow the details. Whereas a couple of decades later, Leon Henkin in, I think he was in Princeton, and he was at the ripe old age of 26. He kind of abstracted on Gödel's proof and gave this new proof of Gödel's theorem, which is now the much more commonly known and taught one. So this is argued contrapositively, the Henkin proof, right? So you assume there's no proof from A to B, and you show that there's a counterexample to the argument from A to B, or you show that it's therefore semantically invalid. And Henkin does this in a more abstract way. He does it by proving, or by building, a maximum consistent set of sentences, or a Henkin model, which is an ultrafilter, and then arguing that there are some things that don't follow from this maximal consistent set. But the key thing about the Henkin construction is that there has to be a maximum consistent set of sentences, and you have to know that it is consistent. And in particular, you have to assume, controversially, you have to assume that nothing could be both provable and not provable. So if you're in a paraconsistent setting where you think there's some possibility of inconsistency, or more strongly, you think that there really are some inconsistencies sometimes, and you might even think that there's inconsistencies about what follows from what, the Henkin proof just seems totally out of reach. It can't, I'd say there's no hope that the Henkin construction can be imitated by any kind of paraconsistent metamathematics. It's just too high tech. So for years, actually, Patrick and I were trying to prove the completeness of just simple logics like LP using the Henkin construction, and we were getting nowhere. And Guillermo came along and kind of had this insight that said, well, wait a second, why are you trying to use these kind of higher level, high-tech constructions that came along after sort of decades of the groundwork being laid in classical logic, and just sort of like jump to the end and get these fancy results? Maybe we should go back to how these results were established originally, how Gödel, say, proved the completeness of first order logic, and look at the baby steps that we'll learn to walk before we can learn to run. And maybe it would be possible to recapture the result by imitating the Gödel result, or rather than the Henkin proof. So that was a pretty good idea that Gia had. The idea for that paper he mentioned earlier, this 2016 paper of ours, What is an Inconsistent Truth Table, where he dug up, this Kalmar's proof for the completeness of propositional logic, and it's a direct proof, whereas most of the proofs you see are contrapositive, but contrapositive arguments don't tend to work for us. So the reason for the title of today's talk, New Proofs by Old Methods, is to go back and use these sort of low-tech arguments, which takes us back to Gödel's original proof from his dissertation. And this proof of the completeness of a first-order logic is direct, and it's constructive, and it proves a classical equivalent of the same fact. So what we're going to argue is that we have, in some sense, the logic invariant core of orthodox metatheory, but that's our interpretation. So that's what we take ourselves to be up to. Now I should just briefly tell you how we're do it, and then Guy is actually going to talk about the mechanics of the proof. I should say that what we were really interested in is the actual, if you like, natural proof that a mathematician using some paraconsistent logic would give. Like imagining for some reason if Gödel had been a paraconsistent logician and had tried to prove his result that way, what would that have looked like, as opposed to spending a great deal of time fussing over the formal system underlying it itself. But let me tell you about the formal system. So we're going to be working with a non-classical logic, which we've memorably titled sub LPQ bottom arrow. I don't know how do you say this? You just shouldn't say
that thing.
This logic, all right? So what is it? It is a substructural paraconsistent logic. So we're going to take as a base, first take Priest's LP, but we're going to take a substructural version of it. So we're going to take LP, but remove contraction from it for reasons that you may be familiar with or not. So it's a weaker version of LP without contraction. But then we're going to look at the first order case. So we're going to add quantifiers for it. We're also going to add to the language, pretty importantly, an absurdity constant, bottom, some constant that can't be true no matter what you think, even if you think some contradictions can be true. And Guy will talk a little bit more about that. And then on top of all of that, we're going to add a conditional operator that obeys modus ponens. So it's a conditional that is not the material conditional. So that's the logic sub LPQ bottom arrow. It's substructural LP with quantifiers and a bottom constant and a conditional. So back in that 2016 paper, we had already studied and proved the completeness of propositional sub LP. So this is just the Q part in the bottom. So we're going to be working with this as a Genson system. I take it we're all pretty familiar with what a Genson system is. This is a Genson system, but kind of with some modifications. We've gone back and modified it to make the proofs work, as opposed to starting with a logic that seems beautiful and then hoping that it leads to proofs. So the Genson system takes as initial sequence identities. It also takes excluded middle because it's a paraconsistent logic. It's supposed to be like LP. So the Priest's LP has the law of excluded middle. So does this. It's got bottom. Bottom is explosive. And then we have found that we need to add further initial sequence for some quantifier behavior that we've struggled to just get quantifier behavior out for free, if you like. So we have some extra initial sequence, which probably means proving stuff like cut elimination about this system is going to be a headache, but that's not what we're doing today. So those are our initial sequence. We've got structural rules. There's weakening and there is cut. There's not contraction. And we're putting up here as well that we have exchange. The order of the premises doesn't matter. Assuming that the premises are something like a multi-set, which is what you would assume in a substructural non-contractive setting, you'd get exchange for free, but we're just putting that there so it's all clear. There's disjunction and conjunction. So disjunction is what's called additive. It introduces on the right in a normal sort of way and introduces on the left in this way. This is argument by cases. This is crucially important for the proof that Guillermo is going to walk you through, to be able to argue things by cases and say, look, either A or B, and A gives you C and B gives you C, so C. That's terribly important for doing real proofs, and I don't know how to get around it. But on the other hand, we are wanting to work without contraction for Curry paradox reasons. So the conjunction that we're working with is multiplicative. That means it introduces on the right, but the contexts gamma and delta have to be kept track of. So we've got two. multiplicative conjunction, additive disjunction, and then we have negation. The idea is to have De Morgan negation. This is a kind of hard to parse presentation of De Morgan negation. This comes from a paper by Font in the Logic Journal of the IGPL from the 90s. He was presenting a Genson system for FDE, which is a weaker logic than LP. So presenting it this way, this gives you De Morgan behavior for the negation and relating conjunction and disjunction. The reason it's laid out this way is because in a Genson system, the rules have to reduce as you go upward. So writing it this way means the thing above the line is always simpler than the thing below the line, but the aim is to just have all four directions of your standard De Morgan laws, which is also important for making the proofs go. Then there's quantifiers. The quantifiers are totally standard, which is probably why we need to add initial sequence to get them to work. But this is just exactly what you would expect from quantifiers. And in particular, it gives you the duality between the universal and the existential quantifier that you'd expect, that if not all X is, not everything is A, it's not A, and vice versa. So there's nothing too special about these quantifiers. So this is LPQ. So that gives you LPQ plus bottom. So that's the theory that we want to prove the completeness of. To prove its completeness, we're then going to have a slightly stronger system on top of it with a conditional. So we're not going to prove the completeness of the system that has the conditional. We're going to prove the completeness of the system that just has the extensional connectives. And then on top of that, to do the work, we're going to add a conditional that introduces and eliminates in a natural sort of way that if you can deduce B from A, then A implies B is derivable and obeys some kind of modus ponens, and also obeys some kind of counterexample principle that if you have A without B, then you don't have A implies B, and that on top of LPQ bottom gives us sub LPQ bottom arrow, which is the meta theory that we're using to prove the completeness with. And that's quite a lot. So then we set out to do some real mathematical proofs in the wild. We kind of do our imitation of Gödel as if for some reason Gödel was using this as his natural logic to use in the background. And we found in order to do that, we also need to help ourselves to something like primitive restricted quantifiers. So in addition to the quantifiers that I mentioned, when we're working with this system, sometimes reasoning in kind of a natural language sort of way, we need expressions that say something like, for example, all numbers are A, or there is a structure B such that B is A. And we need those restricted quantifiers to not just be reducible to the propositional connectives that we showed you. So a universal statement is not just a conditional in terms of the arrow that I had on the last slide. And an existential restricted quantification is not just a conjunction that I had on the last slide. These have to be, in some sense, additional bits of machinery because we need them to obey all four directions of the dualities. I think this is Aristotle's square of opposition. It's just written in more linear fashion, right? That if not all numbers are A, then some number is not. And if there isn't some number that's A, then all numbers aren't, and vice versa. And one would find that if we tried to just get that out using the conditional and the conjunction of the underlying logic, those don't go through for very good reasons, but they do seem needed for the mathematical proofs. So one thing you could take from what we're presenting today, if for some reason you're not completely persuaded that it's important to reconstruct all of reasoning in paraconsistent logic, you could at least take this as kind of a reverse mathematics project and say, what are kind of the minimal resources that a framework to do mathematics would need? You know, what do you really need to get your logic to do something that looks like real mathematics? And we're going to claim that you need some kind of restricted quantifiers. Restricted quantification in the non-classical setting, it's well known that it's a hard problem. We don't have a solution to the problem. One day it would be good to have such a solution. So we'll just say, since we're helping ourselves to these kind of restricted quantifiers for the proof, what we're now going to present is a partial solution. We're going to prove completeness using the substructural logic plus the assumption that some restricted quantification can eventually be worked up. So that's the task that we set ourselves. And now Guillermo is going to tell us how to do it.
Yep. Thank you, Zach. Let me just check that the slides are running. Okay, yeah, it's working. So let me just make one real quick clarification. So in fact, when we say constructive, we are using probably the wrong metaphor from the correct technical point of view, because obviously we are going to be using excluded middle, and that's certainly not a constructive principle. So what we mean by constructive actually is just that it's sort of a direct proof, no? Like that the proof doesn't appeal to any sort of reductio or anything of that sort. So apologies for that ambiguity there. So let me tell you a little bit what we are going to be doing, which is basically following very closely, I don't know if this is visible, this book right here by Hilbert and Ackerman. So this is the Bible for this sort of stuff. So the idea is that, first of all, we need to work with formulas which are in so-called Skolem normal form. And let me clarify, Skolem normal form, obviously this was originally introduced by Skolem, but in a different shape. So a typical Skolem normal form, in the sense that we are going to be using, is a formula which is in EA shape, which means all existentials at the front, all universals at the front, after the existential, and after that only a quantifier matrix, no, a formula that involves no quantifiers whatsoever. So this is what we mean by a Skolem normal form. It comes from Hilbert and Ackerman. However, that's not exactly what Gödel or what Skolem meant by Skolem normal form. So I just wanted to clarify that real quick. So for them, it was more the other way around. For all x, there is an x such and then quantifierless matrix, right? So it was shift around. But it's okay, because either is in a sense equivalent to the other, because by negation principle as an enough duality, the negation of Skolem normal form formula in this sense is going to be a Skolem normal form in the Gödel sense, let's say. Things like this are going to be happening. So this is the first step. We need to put everything in Skolem normal form. However, obviously, it is known that in fact, you cannot put everything in Skolem normal form, right? So one way of phrasing Gödel theorem actually is that if you have any formula which is in Skolem normal form, either that formula is going to be invalid, or you can prove that formula as a theorem. Okay, so this also called sometimes weak completeness, but in this sort of disjunctive form, which is just a material conditional. And that turns out to be equivalent, in fact, to the fact that Gödel actually showed, no? Which is this one below, that if a formula is a negation of a formula in Skolem normal form, either that the negation of that formula is provable, or the formula is satisfiable, right? So it has a model. So that was what Gödel originally proved, and he showed, of course, that that's equivalent to the version that we have above. However, in our setting, that equivalence also holds, right? So these two things can be shown to be equivalent in our setting as well. They are just two different presentations of the same fact, but we are going to focus on the first one. But like, if you would tell me historically, yeah, but what Gödel actually proved is the second one, I would tell you, yeah, that's great, because the second one is just equivalent to the one that I am proving right here. So one thing to notice, as I said, that the presence of Skolem normal form in this sort of argument is sort of an essential feature of the Gödel proof, which is something that makes someone like John Baldwin claim that, in fact, the Gödel proof is less flexible from the classical point of view than the Henkin proof, right? Because we have many logics that have classical semantics, and you can do classical meta theory for those logics, but they do not have Skolem normal form as a theorem, right? So you cannot put every formula in Skolem normal form. For instance, intuitionistic logic is one such example, right? In intuitionistic logic, you cannot put every formula in Skolem normal form. So then the Gödel method in intuitionistic logic would mean that the sort of Gödel completeness would mean something different from what Henkin can obtain. No? So Gödel completeness in the sort of intuitionistic context would mean exactly the way that I have stated it here, right? That for every formula in Skolem normal form, either this happens, or I mean, either the formula is invalid or it is a theorem, something like that. So that's what motivates this formulation that we have of putting this hypothesis that the formula has to be in Skolem normal form. And in our setting, actually, we do not have, as far as you can see, we cannot get every formula in Skolem normal form, because that transformation that gets every formula in Skolem normal form at some point uses disjunctive syllogism. And then it doesn't go through anymore. So that's one caveat, one thing that we have to keep in mind. And that's going to be a hypothesis that we are going to add to every result, right? So now we have, for instance, the Löwenheim-Skolem theorem. And the way that we are going to formulate it is also with the hypothesis that the formula A has to be in Skolem normal form. And then if that's the case, either A is going to be true in every domain, in every model, or A is going to be falsified in some denumerable domain. In particular, a domain with the positive integers as the universe. No? So that's the idea of the Löwenheim-Skolem theorem. And finally, we have, of course, compactness, which in this setting is going to take a couple of forms, again, because of the hypothesis of having things in Skolem normal form. So we are going to say that the logic is compact if for every denumerable multiset in this case, no, because we are working with substructural logics, for every denumerable multiset or set in general of formulas in negated Skolem normal form, either some finite subset of X is not jointly satisfiable. So it's not going to be the case that every formula of that finite subset are going to have a model simultaneously at the same time, the same model satisfying all of them, or else the entire set or multiset is going to be jointly satisfiable. Okay, so that's the formulation, and we have a dual version of that, which is actually, it turns out to be equivalent in our setting as well to the first one, right? So, and this one is saying, well, look, for every denumerable subset X, I mean, any denumerable set X of formulas in Skolem normal form, either some finite subset of X is not jointly satisfiable, or X is jointly falsifiable, or X is jointly falsifiable. And by jointly falsifiable, we mean that all the formulas in that set are gonna go to value F, no? So they're gonna turn out to be false, all the formulas in that set. So again, the reason why we have these dual forms and all of this technicality is because we have this hypothesis of the Skolem normal form around, and then we can present things in this particular way. Sometimes, for instance, the dually countable compact property, this is interesting in some languages where you do not have the negation. For instance, this has been Garcia Matos in a thesis with Vananem, no, on abstract model theory, and they studied this property of dual compactness and what it means for a logic to have this property of dual compactness when there is no negation around. Because of course, versions of compactness with no negation, they come apart, right? In general, in a general setting. So this, the first one is the one that we're gonna be involved with here mostly. So then how do we do this? No, like what is the sufficient amount of mathematics? We saw the logic already, the meta logic that we're going to be using. So what is the sufficient amount of mathematics that we need in order to accomplish this task, basically? Well, first of all, we want some sort of set comprehension principle. No? In this case, we want to work in a naive set theoretical context because, well, that's one of the beauties of having a so-called paraconsistent logic around, no? That you can deal with these sort of axioms that in the classical setting, it would be impossible for you to have around. Now we can have them around. Furthermore, we are gonna make some classical assumptions regarding arithmetic, frankly, no? So we can basically assume, we are gonna basically assume that arithmetic has a reasonable amount of consistency, which basically means, well, like 0 equals 1, this is gonna be a complete absurdity, so we certainly do not want that. And furthermore, we can develop the system of counting in a sort of reasonable way, no? Like, and if you want more details about this, Zach has a forthcoming book doing a little bit of propaganda here with Cambridge University Press, and he goes into some length into developing an arithmetic that should fit our purposes here. Then furthermore, we're going to need mathematical induction. That for any set, of course, if the first element of the positive integers is in that set, and whenever we have some number in that set, the successor of that number is also in that set, then that set is, well, actually, sorry, yeah. So that set should be, that should not be, I don't know why that's a subset relation, no? Like that should be like the entirety of the positive integers, right? Like normal mathematical induction is what you should expect here. So we are gonna help ourselves to that, and we are gonna help ourselves to a recursion theorem, no? That basically we can define functions recursively, functions on the natural numbers in this case, so you could also do it on the positive integers for simplicity in a recursive way. And finally, we're going to help ourselves to the countable axiom of choice in the following shape, that the countable union of finite sets is countable. And the reason why we need this is because at some points we want to sort of enumerate languages and list all possible formulas, I mean, of a certain set, and we want to make sure that in every case we actually have a countable enumeration of such formulas. That's what we are doing here. That's why we need this axiom of countable choice. And this is already, I mean, a sufficient amount of mathematics. You might say, well, I mean, it's already a lot of mathematics. So, okay. So what else? So then what do we start doing? Well, the first thing that we want to do all of these things, obviously set theoretically, as set theoretically as possible. So the first thing that we are going to do is that we are going to define a coding for the formulas of our language, right? So we are going to represent these formulas in terms of sequences of, well, I mean, basically sequences of sets, no? But in particular, you can take these numbers to be sets. So we are going to represent them in this way. This so-called, for every formula, we assign a so-called Gödel set for the formula. And that's going to mean, for instance, this is an interesting thing, the syntax is going to be consistent, right? In the sense that 2 cannot equal 3 on pain of absurdity. Because we are assuming this. We are assuming that no two numbers are going to be the same on pain of 0 equaling 1, and that's going to be an absurdity that we reject, that we are not going to be working with. So the syntax of the language itself is going to be relatively consistent. That's something to keep in mind. And then we define a model in some sort of standard way when it comes to LP. We are going to have relations. This is going to be, let me also say that we are working here with the so-called restricted predicate calculus, or also known as the pure predicate calculus, which means only relational language, right? And no equality. That's what we are working with here. Only relational language, no equality. So then in this setting, we only have to concern ourselves with the semantics of relations. And essentially, a relation is going to be, well, I mean, precisely a relation that goes from a universe, the Cartesian product of some of the universe up to some power n into the set containing the two truth values T and F. And you could take T and F to be 0 and 1. So in particular, that will mean that these truth values can never be the same thing, right? So they are on pain of absurdity, not the same thing. And then we are going to demand that these conditions are satisfied. That if something is true, I mean, for this, that if some tuple is true for this relation R or something like this, then it's not going to be false. And if it's false for this relation R, then it's not going to be true, right? In the sense of the membership predicate here that we are working with. Okay, so then once we have models, we can define, we can extend, I mean, we can define the notion of satisfaction on a model. And for this, we use a little set theoretic trick by Dana Scott that does not require recursion, actually. So it's just a trick that uses a bunch of bounded quantifiers. And then since it uses a bunch of bounded quantifiers and it sort of defines the definition of satisfaction for all the subformulas of a given formula, in order to give you the definition of satisfaction for that particular formula, then it doesn't really need any sort of sophisticated recursion, because you are working within the boundaries of that very same formula that you are in, and using restricted quantification, so you don't really need to to do recursion to that extent as you would normally do. And then once we do this, we play this little trick. It's a little bit of formalism. What we obtain is a satisfaction relation that holds between, well, a set B, which in this case is going to be a sequence of elements from a certain domain, a structure or a model A, and a sentence M. So we are going to say that that sentence M is satisfied by B in the structure A. And this is going to be the typical behavior that you would expect. So it's going to be like this. In particular, we are going to use the restricted quantifiers in the definition of the semantics of the quantifier here. Negation is going to be used in the definition of the negation at the metatheoretic level. And we are going to say that bottom does not hold on any structure, right? So on pain of absurdity, right? So if this would be the case on any structure, we would have an absurdity at the metatheory level. And we really do not want that. So on pain of absurdity, we are not going to have absurdity in any structure. So that's how the semantics is going to look like. And now we can, of course, define the notion of validity. And the notion of validity is just going to tell you that, well, a formula is valid if it's true in all structures. And with this notion of validity, obviously from the sort of Genson system that we introduced before, we are going to interpret a sequence being true in a structure as meaning that if the antecedent of the sequence is true, then the succedent of the sequence is going to be true in that structure. That's the meaning of that concept. So in particular, we are going to say that a formula is, a sequence with the antecedent, this is going to be true in all structure. I mean, if the formula A is let's say we have the sequence empty antecedent, it follows that A, and that A is going to be valid in all structures. That means that A is going to be true in all structures. So that's a way that we're going to be connecting those notions. It's sort of very intuitive, I think. And then we are going to, of course, say that the formula is invalid when we have invalidity because we are using restricted quantifiers that behave in a reasonable way. Once we have invalidity, we can extract the existence of a counter model. So if I have that a formula is invalid, that this restricted quantification is negated here, I can turn it into an existential. I can get an existential, I can get an actual instance of this fact, a witness for this fact failing, basically. But of course, I mean, nothing rules out the possibility that something is both valid and invalid. Of course, this is not going to be some P, and like this P by P here, we mean like a formula rather than a propositional variable, obviously. If it would be a propositional variable and there would be some substitution, then we would get that absurdity is valid, and obviously that's not going to happen on pain of absurdity itself at the metatheory level. Okay, so this is something to keep in mind. So then what is the strategy? So how do we proceed with the proof? So the proof is going to be one general strategy that is going to get repeated in all three proofs. So I'm going to give you the example of the completeness, and then I'm going to go to Löwenheim-Skolem, and then the compactness theorem is actually just a little bit of a more careful version of the argument that we use for the Löwenheim-Skolem. So what is the step number one? Well, the step number one is that we assume that the formula is in Skolem normal form, right? So we can assume that it's a string of existentials, a string of universals, and then a quantifierless matrix here. That's the idea. And now, after we have that, we want to be able to find a counter model, like under certain conditions, we want to be able to find a counter model for this formula in the positive integers, right? So the universe is going to be the positive integers. So how could we possibly do that? Well, first you have to do a syntactic manipulation that is basically going to tell you all the possible ways that I can sort of eliminate this, not eliminate, but like instantiate these quantifiers. So what possible values could these quantifiers take in the universe of the positive integers, right? So we have to describe all the possible combinations that these quantifiers could have in the universe of the possible the positive integers. So that's the thing that we are doing here. First of all, we have to define, since the starting point of this formula is an existential, right? So it's defining a certain sequence from A1 up to AM. So we have to the possible n tuples of the natural of the positive integers in some sort of reasonable ordering. And this is the ordering right here. The idea is that we order all the m tuples of positive integers according to increasing sums and lexicographically within group having the same index sum. Okay, so then that would be something like this. So you always start, if it's an m sequence of m, I mean a sequence of m tuples, you always start with the sequence that only contains ones. Then you go to a sequence that contains all ones except for the last one, which is a 2. Then you move forward in this way. That's the sort of visual representation that you would get from that ordering that I gave you up there. In particular, you're going to have that no integer in the k tuple is going to be greater than k on pain of an absurdity. If it were, then you could get that some number is identical to its successor, and I told you that this is a fact that we are rolling out on pain of absurdity in the meta theory, right? This is one of our assumptions. So that's the ordering that we define, and once we have that ordering, we can go to the syntactic substitutions. So as I told you, we want to sort of find all the possible ways, all the possible interpretations that those quantifiers can have in terms of tuples, no, on the positive integers. And that's the substitutions that we make here. We substitute in m for every k in all possible ways in some reasonable manner. Then we build a disjunction of all those up to some k of all those bits that we have, all of these substitutions that we have defined here. And then for every k, and this is done for every k, right? So for every positive integer bigger than or equal to every positive integer. No, so every number bigger than or equal to 1. And then finally, we are gonna close this ck with a universal, with a sequence of universal quantifiers. So that's the idea here. And as I said, the idea is just to find all the possible ways that you could interpret those quantifiers in the positive integers. And also, this is quantified in this way because we want to get a certain behavior from this dk that is going to become apparent right now. So in particular, this is what we want from dk. We want to have that this sequence is going to be provable, right? So from the dk, I can get that the formula A in question can be provable. From any dk whatsoever, I want to be able to show that. And how do you do that? Well, it turns out that you can prove this without any construction at all, right? So the only principles involved, so meta-theoretically, this is a proof by induction, and at the object logic level, you are going to use principles like this. So some transitivity, some distribution of the universal quantifier, proof by cases that is going to be there. Change of bound variables is something, reflexivity is going to be there, but construction doesn't seem to be needed at all. So this lemma is key, right? So the strategy of the 3 proofs that we're going to see is always, we prove a lemma of this sort, and then we give the actual proof, because the lemma is instrumental. And the actual proof runs as follows. Well, look, you take the formula to be, remember that we want to prove a disjunction, and what we're going to do is actually prove the disjunction directly, right? So how do you do that? Well, you're going to argue, first of all, you're going to help yourself to the law of excluded middle, and you're going to argue by proof by cases. So you're going to get 2 cases. Case 1, this is the fact that this case is hold is just an instance of the law of excluded middle. The first case, the second case is the negation of the first one. And you're going to show basically that if I have the first case, I use the previous lemma to show, first of all, I can use Kalmar's method to prove that, in fact, the antecedent of the previous lemma, this dk, follows as a matter of, because it's going to be valid, then it's going to be a theorem in our basic propositional logic. And then we are going to be able to deduce, using the lemma right here, we are going to be able to deduce that A follows. So that's the way that we're going to get this A, following as a theorem. Because we would have that dk is a theorem, and then we can get that A is going to be a theorem as well, using the previous lemma. And using this Kalmar-style method that we used in our previous paper. Also, by the way, let me say that the strategy, as you can see in this proof, is sort of reducing the problem to the extent that we can to the propositional problem, right? In the sense of completeness, in case 1, we are reducing the problem of completeness to the propositional case. However, case 2 is not so simple. We wish that it were. If it were like this, If all we had was case one, then we would get something stronger than this disjunction. We could actually prove a conditional, right? If case one was the only possibility, we could actually prove a conditional the same way that we did in the previous paper. In the previous paper, we actually proved a conditional, not just as this disjunction. Because it was also like once you had something valid, you could construct a proof. You could write down that one down. So then in case two, what do we do then? Well, in case two, we have to proceed by giving you a counter model. By giving you a counter model on the universe of the positive integers. And the idea is that you're going to get all the falsifying assignments, all the counter models that we get from this case two, and we are going to bunch them together in order to, not bunch them together in an arbitrary way, obviously, but we are going to use them in order to define a so-called master assignment for all the possible, for the entire, for all the predicates and all the possible sequence of elements in the natural numbers, right? And a master assignment that in fact is going to give you back the fact that this formula A is not going to hold, right? So it's going to have a counter model, and it's going to be extracted from this master assignment that we are building here. Okay, so that's a general strategy of the Gödel proof in the sort of Hilbert and Ackermann style. In the Gödel original argument, there are some modifications. It's a little bit different, but we are following here the Hilbert and Ackermann version of it. So that's the idea. Yeah, that's a strategy. So then, as I said, what do you do if you want to get the Löwenheim-Skolem theorem version of the key lemma that we had for the completeness theorem? In this case, actually, it becomes more sensitive to the presence or to the absence of contraction. And in fact, you have to use a certain rule that we have around, which is sort of contractive looking, even though it's not contraction, right? But you have to do something, because in this case, in order to prove this particular lemma, things become more complicated and the absence of contraction shows up a little bit more. But it turns out that we can add this sort of substitute here in order to still get the proof through. And the idea is what? That in this context, we have to show that k many copies joined by a conjunction of not A, of the formula A that we started with, which is in Skolem normal form. So k many copies of the negation of that formula is going to give me the negation of dk. That's what we are proving here. So if you think about it, it's sort of a contraposition in our setting because we do not have contraction, but it's sort of a contrapositive version of the previous lemma that we saw for the case of completeness. And that's the lemma that we need in the case of the Löwenheim-Skolem property. Okay, so yeah, an observation, once more observation. Here we have to appeal to this rule that we call factor following Richard Roudley, but it might have a much more reasonable name. It looks like some sort of monotonicity to me, but okay. So that's the thing. And then how do we actually do the proof of the actual Löwenheim-Skolem theorem? Well,
I'm noticing we're running into our time limit. So
okay. Yeah, so let me just say, so then for the actual Löwenheim-Skolem theorem, you are gonna do two things. Again, you have two cases, and you use the previous lemma in case two, and you use typical proof by cases and reflexivity rule, a very direct argument in case one, right? So actually, it turns out that the contrapositive of the key lemma is used now in case two, which justifies why it's the contrapositive of the key lemma, in contrast to what we had in the case of completeness. And finally, compactness is established by a very similar argument to what you do with the Löwenheim-Skolem theorem. It's just that now you have to consider a full list of formulas, a countable list of formulas, make the substitutions of all those, of all the possible values for the quantifiers in the positive integers, but simultaneously, right? For all of these formulas, so you have to be a little bit more careful on how you define these substitutions. It's a little bit of a tedious kind of process. And then finally, you prove the key lemma, which is a more sophisticated version of the key lemma for the Löwenheim-Skolem theorem. Again, very sensitive to contraction. Once more, you have to use this rule of factor, and that's the way that you proceed, no? And then you obtain the proof by considering two cases again, right? That's a general strategy. And now, sorry if that was a little bit rushed, Zach can finish the
All right. Well, so just to what Gia just said is, I mean, basically it's the same argument strategy 3 times with some modulation for details in each case, but it's this syntactic sort of argument that seems to carry us through. Yeah, or so it seems. So what did we prove? We proved that this kind of paraconsistent metatheory, we can basically imitate the Gödel proof or come close to it. So maybe that suggests that this kind of non-classical framework can be viable without being revisionary. We don't have to say something like, even though it appears that there's a proof of completeness classically, it's not true. We can say, look, yeah, Gödel was right, or this kind of, or the claims that LP is complete, those are right. The big 3 are true, but they're true in this weak sort of sense. It's the sense that Gödel proved, but it's crucially, it's the material conditional sense. So you can make that objection. This is Gödel feeling annoyed that we proved things in a paraconsistent logic, so it made him stand upside down. So we proved these disjunctions. We didn't prove conditionals. Our claim is that that's also what they prove disjunctions, at least for these kind of arguments. And then it's a further step how you want to interpret the facts, but the facts are essentially disjunctive. Like, so in the completeness case, either for any formula that's in Skolem normal form, it's not semantically valid, or else it's proof theoretically valid. Those are the facts as we see them, and I guess we would look forward to your thoughts.
So also let me say one last remark regarding this, that if I remember correctly, in Gödel's original paper, he has a little theorem that is basically showing you that, you know, this disjunctive version is actually a conditional, right? So he has to have this extra little step just to make it clear to people. So yeah.
The end.